Hey everyone, Ethan here. Today I'm going to talk about pyruvate kinase deficiency. You might first ask though, Ethan, why pick this topic? It's a great question. I think it speaks to my own intellectual proclivities. I've always liked mixing topics together, tying divergent ideas and concepts and seeing if they stick. After all, I'm a debater, history major who's in med school. So there you go, pretty divergent topics there in debates, I've drawn on my background in the sciences or history and vice versa. And I just like that mixing of ideas because I really do believe in the value of a diverse skill set and knowledge base. But if we're being more harsh, more self-critical, being broad and mixing ideas isn't always great. Having a broader skill set can often, sometimes, potentially, preclude you from having true mastery over a more limited area of expertise. It also allows you to seem knowledgeable about a lot of things without necessarily having mastered any of them. In that way, it's kind of like using big words, giving this appearance of broad knowledge. And we already know I love using big words. Self-owns aside, that interest in combining concept is what interested me in PK deficiency, or pyruvate kinase deficiency, because it really combines biochemistry, physiology, as well as specific concepts directly from hematology, which we are learning now in class. It's a great chance to tie ideas together, and that's what I plan to do today. And speaking of plans today, what do I plan to talk about today? What is pyruvate kinase? Why does pyruvate kinase matter in the body? What are the clinical manifestations of pyruvate kinase deficiency, and how do we treat pyruvate kinase deficiency? I aim to at least somewhat answer all four of these questions in this video. Let's start with the first one. This is going to be quick. What is pyruvate kinase? Pyruvate kinase is a key glycolytic enzyme that catalyzes this last step of glycolysis seen here. It's an ATP-producing step that converts PEP to pyruvate, and pyruvate kinase is that enzyme that catalyzes this last step. That was easy. Next question. Why does pyruvate kinase matter in the body? And this is going to be, I'm going to go in a little more depth here. It really matters because of this bad boy right here, the red blood cell. The red blood cells lack a nuclei, but they also, in terms of what is important for this, importantly, lack mitochondria, meaning they can't leverage the massive, energetic potential gains from cellular respiration, or specifically oxidative phosphorylation. They're really consigned to glycolysis for making any ATP they need. And glycolysis, of course, is a review you see here. That means by messing up this last step of glycolysis, theoretically, by messing up pyruvate kinase, or PK, we are going to lose out on ATP. Because again, not every step of glycolysis makes ATP. There's only really 1, 2. And by messing up one of the two, you really do have a big cost. And in fact, it's a 50% loss of ATP production for the red blood cell. Additionally, you have to remember that this process of glycolysis is like an assembly line, or perhaps a freeway. You introduce a slowdown at any level by taking away an enzyme, by making one of them operate slower, and you are going to create a traffic jam. You are going to start accumulating precursors, stuff earlier in front of that sort of pinch point. And that means you're going to get, 2PG, G3P, all the like. And we'll talk about this more later, but in response to the anemia created due to red blood cell dysfunction, and also the fact that you are simply just accumulating these glycolytic precursors, you increasingly utilize what's known as the 2,3-DPG shunt. Again, it involves this right here, which is, and this is, it's stated as 1,3-BPG. You could call it also DPG. I looked it up, there's like multiple, like di versus bi, whatever. Regardless, you start using this 2,3-DPG shunt. And the functional consequence is that this creates a rightward shift in the hemoglobin dissociation curve, because shunting to 2,3-DPG causes this curve to shift to the right, meaning that there's more unloading of oxygen in the tissues because of decreased hemoglobin affinity for oxygen. This was always confusing to me, right? Because you might think, wait, hold on, it's a lot of concepts you're tying together. We know that we're using the 2,3-DPG shunt, and we know that's going to cause decreased affinity for hemoglobin. How does that do anything with offloading? I like to think of kids and teddy bears. When I was a kid, I had teddy bears, right? But at the same time, I was a kid, I was losing stuff left and right because I was very irresponsible. However, if I had high affinity to a specific teddy bear, this was my favorite teddy bear, I'm going to hold on to it real tight, and I'm not very likely to lose it. But if this was like a lame teddy bear I didn't really care about, my low affinity for that teddy bear means I'm more likely to lose it. It's the same thing for hemoglobin. This rightward shift means that after it grabs O2 from the lungs, we're going to lose more of it in the tissues because that affinity is going to be lower. It just won't be holding on to oxygen as tightly. So that rightward shift caused by that increased use of the 2,3-DPG shunt is another thing that you're going to notice at a human body cellular level when it comes to this pyruvate kinase deficiency. All right, that was a lot. Let's sort of take a step back here. What do we lose then when we lose out on PK, pyruvate kinase? We lose ATP production. We know that, obviously, because, hello, that's a key ATP producing step. And that loss of ATP production means that the cellular integrity of the red blood cell is compromised. Because, again, what's on the surface of these red blood cells? ATP-driven sodium potassium pumps. And without ATP, you can't drive these pumps, which causes, a suboptimal membrane potential and the like, and that causes red blood cell damage. This red blood cell damage leads to extravascular hemolysis, which I will talk about more later, as these spleens, macrophages sort of recognize these messed up RBCs and destroy them. I'll talk about that more later. But again, what you also lead to is the accumulation of these glycolytic precursors, because you're introducing a pinch point, introducing a traffic jam in this glycolytic freeway. And this works with the anemia that we'll talk about again more later, the extravascular hemolysis, to cause this increased use of the 2,3-DPG shunt, leading to rightward hemoglobin dissociation curve shift, meaning more unloading of oxygen in the tissues. Again, a lot of stuff there. Hopefully at least some of that stuck. This leads us to our third question, which is, what are the clinical manifestations of PK deficiency? The first is just very clearly anemia. Specifically, it's going to be a hemolytic anemia, mainly due to the extravascular hemolysis that occurs when the spleen eliminates damaged red blood cells. And why are these red blood cells damaged? Again, they're damaged because of that PK deficiency. Without having that critical ATP-producing step catalyzed, because that, the pyruvate kinase enzyme is deficient, it's not there, you're not going to have enough ATP to run those sodium potassium pumps. The membrane is going to be all wrong. You're going to have a damaged red blood cell that's going to be recognized and then hemolyzed by the spleen. In terms of test results, in terms of what you actually see, first off, you're going to see a normocytic or macrocytic anemia, right? You have anemia, obviously, because you're lysing all these red blood cells, but it's going to be normocytic because there's no real defect necessarily in red blood cell production, just that we're messing up these red blood cells down the line. You get the macrocytic anemia, not just normocytic, macrocytic potentially, because you have a high reticulocyte response. Again, those are those immature red blood cells, and you have a lot of them because you're trying to recoup the red blood cells you're losing in this hemolysis. Hemolysis, yeah. Sorry. And that high reticulocyte count can look like a macrocytic anemia because these reticulocytes, these immature red blood cells, are bigger than mature red blood cells. You also are going to see increased unconjugated bilirubin and lactate dehydrogenase, LDH. And they're elevated because these are both sort of red blood cell breakdown products. Remember that when you break down a red blood cell, you're going to release hemoglobin. Porphyrin is a component of hemoglobin, which is turned into biliverdin, which is then turned into indirect, aka unconjugated bilirubin. And having so much unconjugated bilirubin from constant hemolysis leading to constant hemoglobin release means that you're going to exceed the liver's capacity to conjugate the bilirubin to make direct bilirubin, meaning that you're going to have, increased unconjugated bilirubin just chilling out there. LDH is going to be increased because LDH, lactate dehydrogenase, is contained in red blood cells and is released when you lyse those red blood cells in the spleen. Because again, we're dealing with some extravascular hemolysis here. You're going to have low haptoglobin. Why? Because haptoglobin is binding to free hemoglobin, and as you create more free hemoglobin from the lysis of red blood cells, you're going to deplete the haptoglobin, the free haptoglobin, because you're going to create these hemoglobin-haptoglobin complexes. So that's why the haptoglobin will be low. And you're going to have a high reticulocyte count because, again, these reticulocytes are like immature red blood cells. You're going to have a lot of them because you're trying to compensate for the loss of those mature red blood cells during the extravascular hemolysis that occurs in PK deficiency. A lot of words there. Hopefully some of that stuck again. Look at me. I'm like a broken record here. But there is one thing I wondered after reading about all of this. Why are we only focusing on red blood cells? My sense was that glycolysis is a fundamental pathway. And yes, while red blood cells are somewhat unique in having exclusive dependent on it, certainly other cells use it too. So again, this question came to my mind. That's not one of the four I came with to start. Excuse me. Does PK deficiency affect cells other than red blood cells? My immediate thought was muscle cells under serious strain, something like the arm seen here, which looks like a carbon copy of my arm. I'm being sarcastic, of course. That wasn't that funny. Glycolysis is necessary, right? When you're pushing arms to their limit, you exhaust the capacity of respiration to power a muscle cell, then you cause that, that lactic acid fermentation as you lean really more on glycolysis when these muscles are under heavy loads. Does this mean then that individuals with PK deficiency have these other deficits, potentially in muscle cells that rely on glycolysis too. Turns out not really, because according to my slapdash research, there are multiple isoforms of the PK enzyme. And the mutation that causes the PK deficiency we talk about here, affecting red blood cells, is distinct from the gene that codes for PK in cells like muscles. So in short, when we talk about pyruvate kinase deficiency, we're talking about specifically a pyruvate kinase deficiency of the isoform that is in the red blood cells, not the ones that are found in the muscles and the brain and the white blood cells and the platelets. So that's separate from the isoforms in the liver and red cells. So just a curious thing that maybe you didn't care about, but it was interesting to me. Last question, how do we treat PK deficiency? The reality is it's really just supportive treatment. One option is folic acid supplementation. Why? Because you really start depleting folic acid as the body tries to compensate for hemolysis. So you're really cranking out those reticulocytes. Remember, that's why the reticulocyte count is high. You're going to need folic acid to do that, to make sure that is not deficient, and you might have to supplement it. Also, we're dealing with anemia, so blood transfusion is always an option. And because we're dealing with extravascular hemolysis, constantly breaking down cells in the spleen, you might get serious splenomegaly, and you might have to do a splenectomy, a removal of the spleen, to treat that. So, 4 questions we talked about today. Did we answer them? The answer is hopefully. What is pyruvate kinase? It's a glycolytic enzyme that catalyzes a reaction that makes ATP. Why does pyruvate kinase matter clinically, or in the body, I should say? The deficiency of pyruvate kinase causes these glycolytic or glycolysis-dependent red blood cells to be affected. Specifically, it causes a loss of cellular integrity because of being unable to run those sodium-potassium ATP pumps on the membrane. What are the manifestations of these pyruvate kinase deficiency? It's really extravascular hemolysis, and as such, a hemolytic anemia. How do we treat this deficiency? Supportive treatment, folic acid, blood transfusion, potential splenectomy. Hopefully that was useful in any way, hopefully. These are my works cited and referenced. Take care. Wish you the best. Have a good one. Bye-bye.